What's up, people? This is Group 1, doing Chapter 15. It's obvious. You can read it right there in the freaking presentation. So, there you go.
Hmm.
Next slide. Let's see. There we go. All right. Roy Rappaport describes one of the challenges of managing the Netflix cloud-based video delivery service, which is a service that streams video at a constant rate to many clients. He says, given a herd of cattle that should all look and act the same, which cattle look different from the rest? Or in other words, given 1,000 nodes, which ones are different? This is important because Netflix wants to provide high quality streaming service to its clients. In order to do that, Netflix needs to better look at how their streams are performing and acting. All the streams act the same, that means all the data should flow the same. But if there is something different, if there's a stream that misses, or if there's data being dropped, or if there's a node out of place, it's important to find that node and treat it. And that leads us into talking about outlier detection. A big key in this is to decide and compute what is considered normal to test against. Just like Netflix, stream content at a constant rate to millions of clients, which means they have hundreds and thousands of servers that provide the streaming process. They had to compute or create a norm for what actual streaming looks like in order to better view outlying processes. These processes can be automatically flagged as bad once you set the normal stream rates, and anything that goes outside of that stream can be flagged as bad. Now, the big key with the Netflix example is their technicians and developers would choose to kill misbehaving nodes instead of trying to save them. Especially in Netflix, where they have hundreds and thousands of servers, they couldn't afford to shift the load over and try to save a server or save one of those nodes. They would instead just kill it and then put in a new one. This saves money and preserves employee sanity by making the process a lot easier to see and to handle. Okay. We're going to talk about mean and standard deviation, or creating a filter using this method by creating a Gaussian distribution. It is simply displayed in the photo here on the slide. Essentially, it is a small hill. You can see data begin to climb, hit a peak, and then go downwards. It is a really simple way companies can create a standard deviation and a method to see outliers, which will enable us to create better alerts. To prevent unnecessary notifications or alerts by increasing the signal-to-noise ratio, monitor what a Gaussian distribution and record the standard deviation so notifications are only sent when it falls under the outlier category of the bell curve. And that'll diddly do it for me.
So now it's my turn to tell you a little bit about instrument and alert and the undesired outcomes that might come from that. The first thing to do is to analyze the most severe incidents in the recent past. And then what you should do, or the next thing to do, is to list the telemetry that could have detected and diagnosed the problem earlier and faster. Then list the telemetry that could have enabled easier and faster confirmation that an effective fix had been implemented. So basically, find the way that you can actually find what's going wrong, or analyze the way that you can find what's going wrong, and then actually start fixing it, just like we talked about in the bell curve back here. Examples of deviating from this, example of deviating from the standard operations include increasing web page load times, server-free memory running low, disk space running low, database transaction times taking longer than normal, and number of functioning servers behind the load balancer dropping. So detecting these deviations can alert and notify of possible failures. Next, we're going to talk a little bit about telemetry with non-Gaussian. Problems that arise when our telemetry data has non-Gaussian distribution. When underlying data doesn't have a Gaussian distribution, alerts can be sent at any time that aren't urgent. In these cases, the properties associated with standard deviations do not apply. One example would be monitoring the number of files downloaded per minute. Most of the time, they will have a very few downloads per minute, but counts frequently spike. This alerts engineers in the middle of the night over something that they frequently can do nothing about. There are ways to detect anomalies with non-Gaussian datasets, and this would be with some auto-scaling capacity at Netflix. This is used Scryer to help predict, this helps Scryer, to predict customers' demands based on historical usage patterns and provision the necessary capacity. He saw that customer viewing patterns were consistent and predictable despite not having Gaussian distribution. So basically, Netflix predicted when its customers would be using services, enabling them to give them the best streaming experience while looking for outliers in between the spikes. And now your turn.
All right. All right. Anomaly detection techniques. So, as was stated before, it's when you use the Gaussian method, it's harder to find anomalies that actually are significant, so you're not being notified by those anomalies over and over again. So when we use anomaly detection techniques to keep track of what was stated earlier with those spikes, you would want to search for events that are not in a specific pattern, but that are also non-Gaussian curves. Let's see. One technique that is used is they search for more incidents in the recent past and kind of map them along the dates. So anything that happens within the specific day of the week or a specific time of the year, it will keep track of that, and then it will detect any anomalies that are outside any normal events that occur during that time. There are a few different techniques that are used to detect these anomalies. One is smoothing, and the other one is, let me find the word for it. It's like Russian or something. Oh, the Kolmogorov-Smirnov test, and the fast Fourier transforms. Let's go to the next slide. Okay. So with smoothing, what happens is they take all the events and they take the average over time, so it's kind of a more smooth line, so they can detect anomalies outside of that smoothed line rather than outside of any of those spikes, which could happen quite often. And then the other one that I was talking about is the Kolmogorov-Smirnov test, which is what I was saying earlier. It's used in seasonal or periodic metric data, such as in a specific time of the week, what would the web traffic look like? What would retail transactions look like, etc. In this graph, we could see, within a few months period, within 1/2 month. Well, what's the timeline there? The 28th to January. Let's just say a month. So as you can see in this graph, within a period of a month, we can see where generally the transactions happen. Well, we can easily see there's an anomaly here and in December, near the end of December, where the traffic is abnormally low. So with this Kolmogorov-Smirnov test, we can easily see that there's a problem where we could have easily see that there was supposed to be a specific level of activity here. There is not. So that's when it can send an event and notify us of any anomaly, so we can detect where the problem is and resolve it before there are too many customer concerns. So in conclusion, to detect anomalies and to better improve our customer satisfaction by catching errors before they become a problem, we can use various statistical techniques to discover outliers and anomalies in our data, which enables us to better understand the ops portion, but also enables dev teams to find errors in code. So with proper alerts, developers can have easier lives and save time and money during the project.
It's for you, Chon. Stay strong, Chon. We love you.
Love John.